Okay, I'm gonna get started. I don't know where the couple people missing are, so they'll get here when they get here. So, chapter 21 homework is due on Friday, the 26th. The chapter 22 homework will be due on October 3rd. The chapter 21 quiz will be on Wednesday, the 24th. Quiz will be in the SI session, just like the previous quiz. If you want to see exactly what mistakes you made on your quizzes, you can see me during office hours or something, and I'll show them to you. But I'm not handing them back. So we were talking about various minerals. We talked about silicate minerals, which are minerals based around oxygen and silicon in a tetrahedron. All the other minerals are non-silicate. And because the silicate minerals are by far the most common minerals, classifying them as silicate, non-silicate is a sort of reasonable way to split things up. Because non-silicate minerals comprise less than 10% of the minerals in the crust. The most common non-silicate minerals are the carbonates, which are something with a carbonate ion. The oxides, which are something with an oxygen. They're an oxide. And then the sulfides, which are something with a sulfur ion. There are also the sulfates, which are something with a sulfate ion, which is sulfur and oxygen. So carbonates have oxygen in them because a carbonate ion is a carbon-oxygen complex. And I think the sulfates do as well. I'm not that great at the naming schemes for these because I've been avoiding chemistry since college at some level. But no, it's hard to keep track of them so much. But generally, these have carbon and oxygen, these have oxygen, and these have sulfur. And then there are pure elements, such as gold and silver, and other gemstones, diamond, ruby, and sapphire, are also all non-silicates. Diamond is pure carbon, as is graphite. There are two different ways to structure pure carbon. Ruby and sapphire are the same mineral, which is why am I blanking on the name of it? It starts with a C, but it's the same mineral. It's aluminum oxide. So technically, ruby and sapphire are oxides. So the carbonate minerals all have a carbonate ion, which is CO3, 2 minus. Bonded with various metal ions. So it's carbonate plus some metal. So things like calcium, magnesium, manganese, iron, and others can bond with carbonate. Calcium carbonate, calcite, is one of the more common varieties. So calcium carbonate is a very common carbonate mineral. It's the primary component of limestone and marble. And it readily reacts and dissolves in mildly acidic water. So one of the ways you can identify calcite is by dripping an acid on it, because it will bubble up. Because carbonates, when they dissolve, release CO2. And if you wanted them to release a lot of CO2, you use a bicarbonate. You may have used baking soda. Baking soda has sodium bicarbonate. And then there's washing soda, that's sodium carbonate. And calcite's a very common mineral component of the rock limestone. And limestone will dissolve over time in slightly acidic water. And groundwater turns slightly acidic from a number of sources. It absorbs carbon dioxide from the atmosphere, and that makes it slightly acidic. And it also picks up stuff as it rotting plant material and other things release some mild acids. And so groundwater ends up slightly acidic. So limestone will dissolve over time in the slightly acidic groundwaters, contributing to the formation of caves. So the vast majority of caves you're going to run into are formed, just the most common type of caves are caves in limestone and what's called karst topography. And they're formed by the dissolving of limestone by underground water. And that makes up the majority of caves. The majority of caves around here are formed that way as well. Like about a third of Illinois is karst topography, so it's fairly common. Oxide minerals formed from the bonding of oxygen ions with metallic ions. So various iron oxides, so Fe2O3, that is not rust, it's one of the other iron oxides. There's several different oxides of iron. Tin oxide, SnO2, and uranium oxide, those are all oxide ores for the respective metallic ion. So most iron ore is an iron oxide that through various processes you convert into iron metal. Most ores are oxides. That's some of the more common type of ores. Yeah. Well, they're not always oxides, but they're usually something bonded. And then sulfide minerals formed through the bonding of sulfur with various metallic ions. So things like iron, lead, copper, and zinc all can bond with sulfur. Iron sulfide is pyrite. It's commonly called fool's gold. Lead sulfite is galena. You may have heard of the town Galena on the western edge of Illinois. And that's a lead mining town because Galena is a lead ore. But also in Galena, you can find a lot of pyrite because, iron is pretty common. There's a lot of sulfur there. Same stuff that makes the lead ore, the lead sulfide. So you get pyrite. So copper, iron sulfide, lead sulfide, and zinc sulfide are all sulfide ores for the respective metallic ions. So here's pyrite, which is iron sulfide. It's pretty readily available too. This is pretty common. And this is fool's gold because it's shiny and gold colored. This is uranium dioxide. This is the most commonly used ore of uranium. And in fact, in nuclear power plants, if you're running a nuclear power plant, you don't use metallic uranium. You just actually use uranium dioxide. You use certain techniques to concentrate it, but it's actually easier to work with the oxide than with the metal. And this is a carbonate. So this is calcite. This is calcium carbonate. It's the primary component in limestone. So the way we identify minerals is we look at both the physical and chemical properties of the mineral. And this is an advantage because there's certain minerals that have the exact same chemical formula, but different molecular structures. Again, the classic example is graphite and diamond. Graphite is carbons in a flat sheet. Diamond is carbons in a three-dimensional lattice. But there's several other things like this. So graphite and diamond are both made of pure carbon, but they're dramatically different minerals. And there's a third form of pure carbon, but it doesn't technically form a mineral. You can have buckyballs, which are carbon-60. You may have heard of graphene, especially in advertising these days. people love to talk about their graphene infused things. Graphene is just single layers of graphite. So pure diamond is very hard, clear, and crystalline. Pure graphite is relatively soft and black. It's used as a dry lubricant. It's used in pencil lead. Actually, in pencils, that's not pure graphite. To make it work better as a pencil lead, they mix it with clay. So it separates out. But you can get pure graphite. They make graphite crucibles and things. So here's the difference. Diamond has a three-dimensional covalently bonded structure. So it's super, super strong and tough. Because every atom is covalently bonded to every other atom, it's super strong and tough. Graphite, on the other hand, all the atoms are in sheets. So it's strong along the directions of the sheets, but it's weak between the sheets. And thus, it's relatively soft. And so it's possible to identify minerals by costly chemical analysis, but often it's not necessary. Many minerals can be identified by just taking advantage of the distinctive physical properties that they exhibit. And these physical properties are easily learned and well known by any serious rock and mineral collector. So things like density, streak, the shape that crystals form, things like that. And a particular physical property that's very distinctive for one mineral might not be that helpful for another. So you need to know what properties identify which mineral. But often it's very helpful for differentiating between things. So one of these is crystal form, the outward form that crystals grow in. So the outward form of a crystal is a visible representation of its internal molecular arrangement. So many minerals have a characteristic crystal form, and if the mineral crystallization occurs in an unrestricted space with just the right components and just the right pressure and temperatures, you get a perfect crystal. This is very rare. Often crystals will grow into each other, so you're stuck with sort of an irregular structure, or crystals aren't going to be totally perfect. You'll get an aggregate of crystals that form with none exhibiting perfect form, but you can usually figure things out. Because where they're growing into an unrestricted space, like the edges will have the right shape. But for an example of these sort of perfect crystals, we have the Cave of Crystals, which is in Mexico, in a mine. This is no longer accessible because this cave became accessible because it was being pumped out for the functioning of the mine it's attached to. And then when they stopped pumping it out, it flooded again.
Deep beneath the earth in Chihuahua, Mexico.
Sorry about that. Wrong side.
Deep beneath the earth in Chihuahua, Mexico, grows a real-world fortress of solitude. In 1910, in the Nica mine in Mexico, the Penoles Mining Company discovered what came to be known as the Cave of Swords. It was an 80-meter-long hallway with beautiful gypsum crystals growing up to 2 meters in length. Unfortunately, the cave was opened up for exploration and later tourism, which destroyed many of the crystals. 90 years later, 2 miners working for the same company stumbled on another cave, except this one was much, much bigger. Nika sits on an ancient fault line above a magma chamber. This heated the groundwater and filled it with sulfide ions. So when this hot sulfide brew met with the cool oxygenated water in the cave, they didn't mix exactly, they kind of sat on top of each other, but the oxygen began to diffuse into this rich sulfide soup, and slowly, at an infinitesimal pace, these crystals began to form. They have been growing for 500,000 years. Today, the largest crystal in the cave is 12 meters in length, 4 meters in diameter, and 55 tons. It is 20 times bigger than any previously known crystal. Amazingly, there's no limit to how big these crystals can get. Given enough time, they will grow ever larger. These are Fortress of Solitude crystals. They are Superman crystals. One big difference between the Fortress of Solitude and the Cave of Crystals is the temperature. The Cave of Crystals is blisteringly hot. It is 50 degrees Celsius or 122 Fahrenheit, and the humidity level is a constant 90%. Even wearing special cooling suits filled with ice and water, researchers were only able to spend about 40 minutes down there. These crystals grew underwater. It's only in the last 20 years this mining company has pumped out all of the groundwater so they can extract various precious ores from the area. But as soon as it doesn't make economic sense for this mining company, the crystals will be resubmerged, returned to their underwater existence. And this is probably for the best, because while it's incredible we get the chance to study them now, that's their natural environment. It's where they grew, it's where they can keep growing. And I think considering how beautiful but also how fragile these are, just knowing that they're under your feet growing ever larger is more than enough. Subscribe here and watch more videos here. This isn't gypsum, this is salt. The Nika project is doing a ton of amazing science around this, including looking at ancient life forms in these crystals and trying to find their closest relative. I've included a link down below if you're interested in learning more about that.
So that cave has in fact been reflooded at this point because the mine ran out of economically viable ore. But you can get enormous, beautiful crystals. And amusingly, certain things you get tons of different varieties of the same mineral that look different. So quartz, for example, quartz is naturally clear. So unfortunately, one thing that is not very good as an indicator of whether what mineral you're looking at is color. There's a few it's helpful for, but often you can have the same mineral appear in many different colors. So here, for example, these are all quartz, all three of these. We have citrine, which is sort of brownish yellow, amethyst, which is a pretty purple, and then quartz, which is just the natural quartz, which is clear. And the colors come from impurities. Tiny amounts of additional elements can have significant effects on the color. And quartz can come in all kinds of colors. There's some really impressive ones out there that have multiple colors in the same crystal. So you have these ones that can look like green and blue and all kinds of things. So the shape of the crystal is very important. That's very useful. So you'll notice that all these crystals have the same sort of hexagonal rhomboidal structure. Another set of properties that's very helpful is hardness and cleavage. Hardness is the ability of a mineral to resist scratching or abrasion. Not necessarily how easy it is to break it, it's how easy it is to scratch it. So, and hardness is generally measured relative to other minerals and materials. There are ways to measure it directly, but usually you just measure it relative to other things in mineral identification, because you can sort, and there's something called the Mohs hardness scale, which measures the hardness of a mineral compared to others, where the softest mineral in existence is talc, and the hardest mineral in existence is diamond. So hardness is relative to other things. And the way you test it is you just try and scratch it with various things, or try and scratch various things with it, because harder things will scratch softer things. So that's how you can help identify this. So diamond will scratch everything. The next down, ruby and sapphire will scratch almost anything, and so on. And then the way that minerals break their cleavage, particularly the way that some of them will break along distinct planes, is a great thing because that reflects the internal structure. So these planes represent planes in the crystal structure where the bonds are weakest. So things like mica peels off in flat sheets. Other ones break in nice cubes. Things like salt, halite breaks in cubical structures. So here's an example of cleavage in mica, peeling off sheets. No, salt forms cubical crystals. It doesn't break nicely, but this is cleavage. And you can have multiple forms of, you could have cleavage in just one direction, like here in the mica. You could have cleavage in multiple directions. You could have cleavage in 3 directions. But sometimes a mineral doesn't have any weak point, and it will undergo what's called fracture. And you'll get minerals that break with rough, arc-like, or jagged edges. And whether it's arc-like, rough, or jagged can tell you something about the mineral a little bit. I think this is flint. Flint does these arc-like fractures. Other minerals break just with rough structures. So this is the Mohs hardness scale is the scale we measure hardness on. So the hardest mineral is diamond with a hardness of 10. Then there's corundum, which is what ruby and sapphire are. It's also why corundum is aluminum oxide. You may have seen sandpaper, or you may have an emery board. Those all have corundum on them because it's so hard, it makes a great abrasive. So if you want to sand something down, or grind away your nails, that is corundum. Then there's things like topaz is 8, and also emeralds. Zircons are 7.5. Quartz is around 7, and a ceramic tile is around 7. A steel file, hardened steel, is around 6.5. So again, the way you compare things on this scale is you try and scrape them with things of known hardness, or scratch things of known hardness with them. And harder things scratch softer things, and that's the sort of general approach. So if you had some quartz, you could scratch it with a zircon, but you wouldn't be able to scratch it with a steel file. Then there's orthoclase, which is potassium feldspar, is 6. Glass is like 5 to 6. Apatite, which is 5, it also is the same hardness as tooth enamel. So anything you can scratch with your teeth is less hard than 5. Platinum is around 4.3. Fluoride is 4. But like iron or nickel, unhardened iron or nickel is also 4, like a nail. A copper penny is around 3.5. Calcite is 3. Gold is 2.8. The human fingernail is 2.5. Gypsum is 2. Lead is around 1.5. And talc is 1. And then sodium metal, which is incredibly soft, is about 0.5. So there are other ways to identify sodium metal, because it also does things like react with water violently. So Fracture is irregular or random breakage of a mineral. When a mineral breaks in a manner that is not a flat surface, but is either an irregular breakage or those smooth arcs. Those are the two types of fracture. And then color is the property of reflecting a particular wavelength. This is probably going to be the first thing you notice, but color is not actually that useful of an identifier for minerals. So as an example, quartz can occur in many, many colors. So things like clear, milky, smoky, yellow, purple, red, orange, pink, blue, green, like almost any color you can get quartz in. However, streak, the color of a mineral in powder form, is a much better indicator of the mineral. So if you scrape a mineral on a ceramic plate or a rough stone, it will leave behind a streak. And although an intact mineral sample may exhibit several colors, the streak color will always be the same. And you may have heard of a touchstone. A touchstone is a tool for measuring streak of precious metals. It's a rock that you rub something you think is gold on and check the streak to see if it looks right. So for example, if you had gold in pyrite, fool's gold, the streak of gold is gold colored, but the streak of pyrite is like black, dark brown black. So you want it there, but the streak will always be the same. Now, luster is how a mineral's surface reflects light. So they could either be metallic or non-metallic lusters. So metallic lusters appear like a polished metal. Non-metallic lusters could be like vitreous or glassy, adamantine, or sort of diamond-like, pearly, or which is what opal is. Greasy like talc, or earthy or dull like clay. So here's an example with hematite. Hematite has a red-brown streak. These are two examples of hematite. You can see they're different colors, but they're the same mineral, and they leave behind the same color streak. So streak is usually done on a ceramic plate like this. That's part of why the ceramic plate was on the list of hardnesses, because it's a thing that geologists tend to have, because they're using it to measure streak. And here are some examples of metallic and non-metallic lusters. So limonite over here has a non-metallic luster. It looks like a rock. But pyrite has a metallic luster. It's shiny like metal. A better identifier of pyrite, there's a couple. One, it forms little cubes, which gold doesn't. And two, the density is wrong. Gold is denser than pyrite. So that's the next thing, the specific gravity, the density, the ratio of a mineral's weight to the weight of an equal volume of pure water. That's the density in grams per cubic centimeter. So many minerals have specific gravities between about 3 and 4. They're 3 to 4 times as heavy as water. But some minerals have significantly higher specific gravity. Galena, lead sulfide, has a specific gravity of around 7.6. Pure gold has a specific gravity of 19.3. And it's probably the densest thing you're going to run into on a regular basis. I mean, it's not the densest thing out there. There are denser metals. Osmium is the densest pure element, for example, but osmium is super rare. Another property that shows up is something called fluorescence. Fluorescence, if you shine a light on certain chemicals, they will fluoresce or glow. So if you shine a UV light on many minerals, they will glow in the visible light range. This is in fact how the lights above your head work. There's a tube that has mercury vapor in it, that it's generating primarily UV light through through emission, like a neon light, but in the UV. And then it's surrounded by a fluorescent powder that, when it absorbs the UV light, re-emits a bunch of colors that appear white to us. So here's a short video about why some minerals glow, why they fluoresce. The most famous thing that fluoresces is fluorite. It's literally what the term is named after. Fluorescence is named after the mineral fluorite. And there's a really nice exhibit of fluorescent minerals at the Field Museum. There's like a case with a UV light in it, so you can see them fluoresce.
Hello, my name is Deborah Wilson. I'm the collection manager for the section of minerals here at Carnegie Museum of Natural History. Today I'm going to show you an interesting hyalite opal. Most hyalite is very fluorescent, which means under ultraviolet light it'll glow. I've actually pulled a couple of samples of fluorite, and fluorite was the first mineral species that fluorescence was discovered in, so it was named after the fluorite. Certain specimens will have what we call activator elements in them that when the ultraviolet light is shining on it, it kind of excites the electrons and they move up to a higher state, and as they're moving back down, you'll see the light in your visible spectrum. Here are two specimens of fluorite from England. You'll notice that they are different colors in natural light, but you'll see when we put them under the ultraviolet light that they fluoresce almost the same identical color. This is a vug, is what we call kind of an opening in the rock where these minerals are growing. There's little quartz crystals and chalcedony, which is a variety of quartz, that have a coating of hyalite opal on them. And this is from the Candelaria mine in Sonora, Mexico. So let's take a look and see what this hyalite opal looks like under the UV. This is shortwave ultraviolet, which most species that fluoresce do the best under shortwave. Some things will also fluoresce under long wave. Some will do either one or the other. Hyalite normally does shortwave, but we'll take you up to Hillman Hall and show you hyalite opal that actually fluoresces under long wave. So if I have a little ultraviolet pen, it'll penetrate the plexiglass and will actually make this fluoresce. Now this one also is so highly fluorescent, it will start glowing under natural sunlight. This deposit of hyalite opal was discovered in Zacatecas, Mexico in 2013, and it's all been mined out. There's no more coming out. This piece of rough is got little globular growths, it looks like, that you'll be able to see better when I make it fluoresce. And this gemstone is the second largest stone that was cut from everything that was recovered there. So let me show you how it fluoresces. It turns this bright green. You can see it a lot better on the matrix, and even the gemstone just pops when you hit it with the UV light.
If you like this video, please press like and subscribe. And also, please visit us here at the Carnegie Museum of Natural History.
So fluorescence basically occurs, something jumps up like multiple energy levels, and then it takes multiple steps on the way down. So the light going in is more energy, and it gets broken into lower energy, longer wavelength light that are visible. So you put in UV and you get out visible light, basically. So So some properties to identify minerals: the crystal form, the size and shape of the crystal faces. Is it a tetrahedron, a rhombohedron, etc.? The hardness, the ability to resist scratches. It's a scale from 1 to 10, with 1 being the softest mineral at talc and 10 being the hardest at diamond. Cleavage, the tendency to break along definite smooth planes. Fracture, the way the mineral breaks. Does it splinter? Is it irregular pieces or is it shell-shaped forms? The color, the reflected wavelength of light. This is probably the weakest and least useful tool. The streak, which is the color of the powder of the mineral, which you usually get by rubbing it on a ceramic plate. So it, like a rough ceramic plate that leaves behind a streak. The luster, which is the surface appearance in reflected light, is it metallic or non-metallic? And the density, the specific gravity. And then there's also things like fluorescence, whether it fluoresces. There's a few other like random properties that aren't on this list that are often useful. There's like bifurengence is a property that minerals can have, which is where incoming light will be split into two. You can do some very interesting things. So those were minerals. We talked about minerals. There are also rocks. A rock is a natural, solid, cohesive aggregate of one or more minerals. So basically, minerals are just individual substances, and rocks are structures made of them. So rocks are made of minerals. Technically, rocks are made of minerals and mineraloids, just because we would really like to be able to refer to a bunch of things that are not quite technically minerals as rocks, like obsidian and coal and stuff. But so there's a few other things that geologists will sort of let be called rocks, and they'll categorize the stuff that goes into them as mineraloids. They don't quite technically qualify as minerals. But this is just like, so like, because in general purposes, if you saw some obsidian, you'd call it a rock. Even though it is technically not a mineral because it's a glass. Or if you saw some coal, you'd think of that as a rock. But that's the definition of a rock. The natural solid cohesive aggregate of one or more minerals. Rocks are mixtures of minerals, while minerals are composed of individual elements or compounds with specific chemical formulas. So rocks generally are made of more than one mineral. Some rocks are made of just one, but they're made of like, usually they're made of multiple. They can be made of multiple minerals as well. And different types of rock compose the vast majority of the Earth's crust. And a lot of the times when we look at a rock, we don't see the individual minerals. Sometimes you can. So like in granite, granite has relatively large crystals of its minerals, so you can often see the different minerals as different colors. But a lot of the times the crystals are too small to see just with your eye. And so it all sort of blurs together. Rocks can be divided into 3 major types as a result of the way they form. Igneous, which means born of fire, which forms from molten rock. If it was molten and solidified, that's an igneous rock. Sedimentary. Sedimentary rocks are formed from sediment, material broken off of other rocks that is transported somewhere else and settles. Also, you have minerals that were dissolved in water and then evaporates or something like that. There's some other ways you can get sedimentary rock, but that's the general idea. They're formed from previously existing rocks that have been broken down in some way. And then metamorphic rocks are rocks that existed as one type of rock and then are changed. They metamorphose. They're transformed. So you have rocks from fire, rocks from broken up bits of other rocks, and rocks that are transformed. So an igneous rock is a type of rock formed from molten material that has been cooled and solidified. And molten rock has two names depending on where it is on Earth. If it's underground, it's magma. So molten rock material that originates deep within the Earth is magma. So rocks that solidify from a magma beneath the Earth's surface are called intrusive igneous rocks. And granite is an intrusive igneous rock. And if that rock breaks the surface and comes out, it is lava. The only difference between magma and lava is location. Magma becomes lava the instant it leaves the ground. So rocks that solidify from lava at the surface are called extrusive igneous rocks. Intrusive igneous rocks form inside the Earth. Extrusive igneous rocks form external to the Earth. So here are some examples of extrusive igneous rocks. So this is basalt. This is solidified lava. Like this is just the surface of solidified lava. You can see the crystals are really tiny in these. That's because they cool very quickly. And the fastest cooling lava forms like glass. Cools so fast you don't even get crystals. And that's how you get obsidian, for example. And here is an intrusive igneous rock. Notice how the crystals are much bigger. And this is granite. So granite has those nice patterns you can see of different minerals because the crystals formed over a longer period of time, so had longer to grow big and got nice and big and attractive to look at, which is why people make their countertops out of it. Also because it's hard. So those are igneous rocks. We'll go over them in more detail later. Sedimentary rocks are rocks that form at or very near the surface due to the compaction and cementation of sediments. Sedimentary rock is when you have lots of little bits of rock that have broken off, weathered away from somewhere else. They're brought to another location, and then they're compacted under the weight of all the material above them and cemented together, basically glued together. We make artificial sedimentary rock all the time. It's called concrete. So concrete is basically artificial sedimentary rock. You take a bunch of aggregate, a bunch of rocks like gravel and sand and stuff, and then you bind it together with cement. You cement it together. The cement in concrete is treated to go through the process very quickly. The process that actually occurs for forming sedimentary rocks is much slower, but it's a similar process. So the sediments that compose sedimentary rocks come from three general sources: rock fragments that are due to the erosion of pre-existing older rocks that make things like gravel, sand, mud, silt, like all the dirty stuff, all the like rock you have around. Minerals chemically precipitated from solution, and then plants or animal remains, fossils, can also be a significant part of sedimentary rock, especially if those plants or animals extract minerals from solution to form hard parts of their bodies. So that's the one like funny line when it comes to minerals, because certain types of sedimentary rock are primarily made of the bodies, the hard part, minerals precipitated from the ocean and formed into like the hard parts of creatures, and then they die. And there's a lot of limestones that are made of, shells and stuff, and tinier creatures. There's also some other types of stone that are made of like stuff that's primarily the dead bodies of small animals, living things. So, and then there are certain things that occur from like evaporates where dissolved mineral, well, there's various things that can cause dissolved minerals to precipitate on us. And then there are metamorphic rocks. Metamorphic rocks are rocks that form when one rock that exists moves somewhere with different conditions than it was formed, usually a high heat or high pressure, and it is transformed. So here we have some gneiss. And this gneiss could have originally been like sands, like mudstone or slate. This is a pretty thoroughly transformed rock. So metamorphic rock is formed by the alteration of a previously existing rock due to the effects of pressure, high temperature, and or a chemical change. And metamorphism usually occurs well below the surface, but not so low that stuff would melt. I'm wrong. That is not gneiss. That is schist. I got them confused. They're both in a chain of metamorphism. Another famous type of metamorphic rock you may have heard of is marble. Marble is transformed limestone. It started as limestone. Very high heat is applied to it, and it recrystallizes and becomes a more consistent mineral, which makes it good for making statues. And then uniformitarianism. So beginning with the Scottish physician scientist James Hutton, scientists started to realize that ancient rocks were formed in the same way as modern rocks. So since they were formed the same way, they can be interpreted similarly. So the idea of uniformitarianism is that the processes that are making rocks today are the same as the processes that were making rocks far in the past. So that geologic processes occurring today operated similarly in the past and can be therefore used to explain past geologic events. So the present is the key to the past. This principle is mostly applicable. There's a few exceptions. There are certain types of rock that just, the conditions to form them don't exist anymore on Earth. They formed during certain portions of the history of Earth where, say, it was much warmer, there was a lot more oxygen or something like that. Or much warmer and a lot more certain types of life and things. So one of the most common types of iron ore, the conditions to form it don't exist anymore. But the general idea is that what you see happening today is more or less what was happening in the past, is a good solid approach. The present is the key to the past. So if you see rocks, if you dig up some rock and it looks just like a rock that you know how it formed in the modern day, you can say, okay, I know how that rock formed because it formed just like the rock that I saw forming at this volcano. So something similar to that had to have occurred. So James Hutton realized that rocks in the Earth's crust were continuously being formed, broken down, and reformed. There's this cycle where rocks change and move and are transported about. And these are the same processes that are responsible for the three types of rocks. Igneous rocks come from molten rock that had to have melted somewhere. Sedimentary rocks come from the broken down pieces of other existing rock. Metamorphic rock is transformed rock that is either igneous or sedimentary or other metamorphic rock. And this whole process of one rock changing into another rock and rocks moving around is called the rock cycle. So the rock cycle is a series of events through which a rock changes over time. It can go between igneous, sedimentary, and metamorphic forms. And it doesn't always just go igneous, sedimentary, metamorphic, and back. It can, any type of rock can transform into any other type of rock, kind of. So sedimentary rock can melt and become igneous. Igneous rock can metamorphose to become metamorphic. It can melt and become igneous again. both metamorphic and igneous and sedimentary rocks can form sediment to form more sedimentary rocks, and pretty much any rock can metamorphose. So the processes are things like deposition, transportation, weathering, melting, crystallization, cementation, compaction, etc. So here's sort of a rough guide of the rock cycle. So all rocks can weather and erode to become sediment, which they then compact and cement to become sedimentary rock. All rocks can melt to become magma, which can cool and solidify to become igneous rock. Sedimentary rock is that kind, they just didn't draw the arrow there. And then all rocks can undergo heat and pressure to metamorphose to become metamorphic rock. And Hunt also realized that these processes that form and break down different rock take enormous amounts of time. And he hypothesized the Earth to be very old. So this led to some interesting discussions, because around the same time, there were some physicists who did some calculations on how they thought the sun was powered. And the number they got for the age of the sun was the possible total age of the sun was a lot smaller than the number the geologists got for the age of the Earth. And central to the science of geology are the following three concepts. This principle of uniformitarianism, where what we see happening today, similar processes happened in the past. What we see there, this rock cycle, the constant transformation of rocks from one type into another, and the recognition that the Earth is very old and has had a lot of time to do all this geological stuff. The Earth's about 4.5 billion years old. And so the energy from the rock cycle comes from two main sources. Igneous and metamorphic rocks are fed by plate tectonics. The plates moving around, heat rising up, that melts stuff, applies pressure, that drives the creation of igneous and metamorphic rocks. Sedimentary rocks, actually, the energy comes from weather, which is driven primarily by cycles of movement of water and such caused in the atmosphere, caused by weather, which is driven by the energy from the sun, primarily. So here's a short video about the rock cycle.
Okay, let's take a quick look at the rock cycle. Here's a diagram showing the rock cycle in the Earth's crust. This particular diagram can be found in the New York State Earth Science Reference Tables. What it shows are the different types of rocks and how they can change over time. Let's go through a quick example. Here is a chunk of an igneous rock known as granite. You can see it's made up of intergrown crystals of potassium feldspar and quartz and biotite, and that's what gives it its speckled look. Now, as we mentioned, granite's an igneous rock, which forms from the solidification of melted material, magma or lava. Granite happens to form deep underground from the slow cooling of magma. But the question we want to look at now is, well, what can happen to this igneous rock over time? And there's a handful of possibilities. The first thing that could happen is our granite could be lifted up, forced up from beneath the ground, where it's exposed to weathering and erosion. The wind, the rain, the ice, these forces break this rock down into little small pieces called sediments. So now our granite has been broken into small pieces of granite. Now these little small sediments can be deposited and buried and then compacted and cemented together to form a brand new rock called a sedimentary rock, like this piece of sandstone. So simply by weathering and eroding the granite into sediments and then squeezing the sediments back together, you've converted your igneous rock into a sedimentary rock. But that's not the only thing that can happen to our igneous rock. What if it is pushed even deeper underground by the movement of Earth's tectonic plates, and in so it is exposed to intense heat and or pressure, causing it to metamorphose or recrystallize into a metamorphic rock, like this piece of gneiss seen here. So, with the simple addition of some heat and pressure, we've turned our igneous rock into a metamorphic rock. But there's still one more option. What if our igneous rock is exposed to intense heat, causing it to melt and return into liquid state of magma? Well, it can then, of course, cool and solidify again, giving us another igneous rock. But maybe this time it will cool quickly and give us something with smaller crystals or maybe no crystals at all, like this piece of obsidian. So what you can see is that on the rock cycle, any rock is able to turn into any other rock when exposed to the different processes in and on the Earth's surface. Remember, we start with these three types of rocks. These are our three classifications. And from them, we can go to anything else. Again, let's look at the igneous rock, right? Igneous rock, we know, forms from melting into magma and solidification. But remember, it can melt again, and that process can happen over and over and over again. So I can have an igneous rock that becomes igneous again, maybe a different kind of igneous rock. But any rock can melt into magma and form an igneous rock, as seen on the chart. Sedimentary, metamorphic rocks, they can all be melted and ultimately result in an igneous rock forming. Well, let's look at the sedimentary rock. Now remember, these form from sediments that have been deposited and buried, and pressure causing them to compact and cement together. But of course, any rock can be weathered into sediments, and therefore any metamorphic or igneous rock can become a sedimentary rock. Finally, we have our metamorphic rock, and remember, these form when rocks are exposed to intense heat and pressure. But of course, that process can take place with any type of rock, sedimentary, igneous, or even metamorphic rocks. So the key idea behind the rock cycle is the fact that any rock can become any other kind of rock. It can even become itself. Change is always taking place. It's generally slow over many millions of years. However, the results can be impressive. Thanks.
So let's start with talking about the formation of igneous rocks. So igneous rocks form from the solidification of molten material that generally originates from beneath the surface of the earth. Unless you're in one of those couple of labs that make artificial lava to study how it moves and flows and forms rock. There's a couple of places that do that. They melt down rock and pour it to see how lava works. But magma, molten material. Magma is molten material that is beneath the Earth's surface. So molten rock is magma until it breaks the surface of the Earth. And lava is molten material at the surface of the Earth. So the term lava is also used to describe the cooled igneous rock that forms from lava flow. So, because it has, like the surface rock that forms. So if we assume the Earth was originally molten, which is a reasonable assumption because it was formed by a bunch of space rocks smashing into each other and getting really hot, the first rocks on Earth were formed as the outer crust slowly solidified billions of years ago. So the very first rocks that formed were igneous rocks. And since these initial rocks were formed, various geologic processes have modified, covered, or eroded most of these ancient materials. And it's estimated that approximately 80% of the Earth's crust is composed of igneous rock. Now, about 75% of the surface of the continental crust, just the surface of the crust is covered with sedimentary rock. It's just not very thick. So basically, all the sedimentary rock is a thin layer on top of the igneous rock beneath. It's all the bottom part of the crust. The lower layers are all igneous rock. Now, igneous rock can be divided into two basic categories. Did it form above ground or underground? Extrusive igneous rocks are igneous rocks that cool at the surface of the earth, generally due to some form of volcanic eruption. The most common type of extrusive igneous rock is ocean floor basalt. It's constantly being formed along all the mid-ocean ridges, where lava, deep magma rises up, comes out the crack, and immediately cools in the ocean, forming ocean floor. That's the most common form. There are other forms. We'll go over them. But basalts are the most common form of extrusive igneous rock. You also see basalts in places like volcanoes, like the volcanoes in Greenland and the ones on Hawaii, all produce basaltic lava. Now, if you have rock material that's coming from more shallow, that has more silicates in it, you get other things. You can get anthracite, I think. Let me see. No, rhyolite, that's it. Anthracite's in the middle. And then there are intrusive igneous rocks. These are rocks that are cooled somewhere beneath the surface of the earth. The most common form of these is granite. So intrusive igneous rocks only appear at the Earth's surface due to the overlying layers being eroded away. So you do get granite at the surface, or intrusive igneous rocks at the surface in certain places. That's because the overlying material has been worn away. So the Rockies, that granite was thrust up, and basically the overlying sedimentary layers all eroded away. So you have very hard granite mountains, things like that. So the difference between intrusive and extrusive is how quickly they cool. Extrusive rocks are exposed to the outside, so they cool very quickly. Intrusive rocks are buried underground, so they cool quite slowly. So intrusive cools slowly beneath the Earth's surface, while extrusive cool quickly at the Earth's surface. And this affects their properties. They're classified according to two criteria: intrusive or extrusive. That determines the texture. So the texture, the size of the mineral grains, the crystals in the igneous rock, is determined by how fast they cool. The longer they take to cool, the bigger the crystals. So things that cool really fast, tiny crystals. Things that cool more slowly, big crystals. Things that cool at two different speeds, you can have a mixture. And then the mineral composition refers to the specific type of mineral crystals in the rock. So there's sort of two general categories of mineral composition. There are felsic rocks that are like granite. They have a lot more silicate minerals. And then there are mafic rocks, which have less silicate minerals and more heavier minerals and more like iron and magnesium in them. They come from deeper in the mantle, deeper magma, hotter, deeper magma. And they are darker, and they form things like basalt and gabbro if they're intrusive. So the texture, the grain size of an igneous rock is determined primarily by the cooling rate of the magma or lava. If magma cools very slowly deep within the earth, you get large crystals that form, such as granite. When it cools rapidly, large crystals don't have sufficient time to form, and you get something like basalt. And if it cools extremely rapidly in water or ice, you get no crystals, and you can get a volcanic glass like obsidian. So the same starting material, if it cools slowly, can form something like granite. And if it cools quickly, you get something like rhyolite. And again, if it cools quickly, you get basalt, and if it cools slowly, you get gabbro. So here's a granite rock in Yosemite, California. This has been, the overlying layers have been worn away. So intrusive rock cools at depth, so it cools slowly, its texture is coarse. An example is granite. Extrusive rock cools at the surface, its cooling is rapid, its texture is fine like basalt. And a super extrusive, and some extrusive rock cools very quickly in air or water, very rapidly, and its texture is glassy like obsidian. And the other aspect is the composition, the minerals it's made of. And the best indicator of this is actually its color. Because the amount of silica within an igneous rock can be used to classify it according to its composition. If the magma or lava is high in silica, minerals form with abundant silicon, sodium, and potassium, and these rocks are referred to as felsic. This is things like granite. If granite is felsic, it's light in color. Well, when the magma or lava is low in silica, you get minerals rich in iron, magnesium, and calcium that are dark in color, and these are referred to as mafic. And the most common mafic minerals are basalts, but if you have slow cooling mafic rock, you get gabbro. If you have fast cooling granite, felsic rock, you get rhyolite. And then there's an in-between, which is andesite. And the dark, low silica rocks are denser than the light, high silica rocks. The continental plates are composed of the less dense, high silica rocks, and therefore stand high above sea level, while the oceanic plates are composed of the more dense, low silica rocks, and therefore rest lower, usually below sea level. Generally, high silica magma is hotter, low silica magma is cooler. And high silica magma comes from deeper. Low silica magma comes from higher up in the stuff. And the medium in between rocks are andesite, because you could have stuff in the middle. So here's sort of the andesite and diorite are there. So here's sort of a table for these. High silica content, color is mostly light. If it's extrusive, it is rhyolite. If it is intrusive, it is granite. This is primarily found in the continental crust. Medium silica content is mostly dark. If it is extrusive, it is andesite. If it is intrusive, it is diorite. This is found in volcanic iodides or subcontinental mountain chains. And low silica is dark. No, the low silica is about 40 to 50% silica. There's still a lot of silica even in low silica rock. If it's extrusive, which is the most common type, is basalt, and if it's intrusive, it is gabbro, and this is what forms the oceanic crust. And it also, what you see from certain volcanoes, shield volcanoes, or other, basaltic flood basalts and stuff, you get from places like Hawaii and Iceland. Those volcanoes are putting out basaltic lava, and that cools to form basalt. So most of Hawaii is made of basalt because the shield, because the lava there is very low silica. So here's, this is the oceanic crust. It's much thinner, but it's denser. And then the thicker continental crust. This is like 2.7, 2.8 grams per cubic centimeter. This is more like 2.93 grams per cubic centimeter. And then the mantle is a little denser at around 3.3 grams per cubic centimeter. So continental crust is thicker than oceanic crust. It's also more variable. It's much thicker under mountains. So overall, the continental crust is less dense and thicker than the oceanic crust. which is more dense and thinner. That's time to stop. Any questions about any of this? We'll be looking at a bunch of these rocks in our next lab. So that's on rock identification. But if you want to see examples of them, you will. Yeah. And those dates aren't right because I haven't updated that announcement set yet. So I'm going to stop sharing. And